Oh, quadratics, you're better than other types of math. Linear relations are boring, but you are exciting. You help me to solve problems in physics and chemistry. Quadratics, we thank you. All together now. Oh, quadratics. All right, you guys suck. Anyway, a quick reminder of what we mean by quadratics. Who can remind me, a quadratic equation is just another way of saying what shape on a graph? Yeah, a parabola, right? Something like this. And the quadratic equation helps us find two specific points, right? It lets us know that for any quadratic relation, we can find the roots of it, right? So if you recall, if we put any parabolic expression in the form ax squared plus bx plus c equals 0, we can say for any equation like this, we can say that x will be equal to... Do I have to sing the song? I don't even know the song. I know Calford does the song. Go.
X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a.
Guys, that was beautiful. I can genuinely say it brought a tear to my eye. But very good. Okay, guys, I don't want to put you all on the spot. Whose quadratic song was better?
Thank you.
All right? All right. Kartik, you take this round. You're all dead to me. And let's go. Is it because it has the snappy ending? The all over 2A. Is that does that really sell it?
It's the pop goes to weasel.
I understand that. Thank you. But no, you know what? I say that, but I was embarrassingly old when I realized all the songs are the same melody. All the kids, they're all the same.
Yeah.
Twinkle, twinkle, little star, H-I-J-K, L-M-N-O-P, and you're like, oh, same melody. Ba ba, black sheep, H-E-N-E, they're all the same. Different one, but it shows up in other ones too. Yeah, they're just thieves. They're just melody reusers. And as a kid, you don't even realize. You don't even realize, team. Okay, so
What would you like?
listen. This is what we're going to have to use later on. It's okay. We're going to use this tool, but when we have to solve for an expression like this, we just plug it into that, we go. We'll get a bit of practice doing that with a calculator. If you don't have a calculator now, before I shout at you, yeah, you can hand those back if you like. But let's just wait till we're through this. I want people focused. So before I shout at you later, make sure you have a calculator in front of you. Actually, I mean you. I don't mean someone else. If you need to go get one, go get one. So I want to imagine we have this reaction here. We have two hydrogen iodide molecules, all right? And that can go in an equilibrium to form hydrogen gas and iodine gas, all right? There it is. What we're going to say is, what if we started out with 0.100 moles per liter of this stuff and none of the products? Does that make sense? All right? So we start out with that and we have no products present. We have none of that. We want to say this is not at equilibrium yet, right? We know that. But we know it's going to move to equilibrium, right? So I want to make a little table here. And the table we're going to make is typically called an ICE table or an ICE table. But that's because we're going to look at the initial state, all right? So how does this start out? Novak, it's here, I think, if you need it. Oh, no, it's not. That's yesterday. Okay. And then we can look at how things change. And finally, what will the state of things be at equilibrium? Does that make sense? Okay. So in this case, we have hydrogen iodide, which is a gas, right? And we have hydrogen gas, and we have iodine gas. These are the things we have to keep track of. And we said to start, how much hydrogen iodide gas was there? What was its concentration? 0.100 molar. Okay? And what were the concentrations of hydrogen and iodine gas at the start? Question tells us. Yeah, the question says we have no products. So we're going to say 0 molar and 0 molar. All right, how's that feel? Not too bad? Just bad enough? All right. Now, this is going to change, but we don't know by how much. In math, what would we do if we wanted to say that we know that the concentration of hydrogen iodide, is it going to go up or down? It can only go down, right? Because we're starting with all that and no product. So the concentration of this has to go down. On the other hand, the concentration of hydrogen and iodine, is it going to go down or up? Yeah, there's nowhere to go but up. It's currently at 0. So this is a pretty easy question to start with there. And they can't just be random numbers because they're tied into each other. What do we know from the equation? How much is HI going down by? Well, every time we go down this equation, it's going down by 2 moles, right? How much is H2 going up by? Well, every time we go through this equation, it's going up by 1 mole. What about I2? Going up by 1 mole. So really the only question is, how many times does it go through this reaction? We could let that be a variable. And in math, what's a nice letter for a variable? X. So we could say, well, let's just say that the concentration of H2 is going to go up by X, some random value. We don't know. We don't know how much. But what we know is, if that's how big the concentration of H2 grows by, how much is I2 going to grow by? Well, for every mole of H2, how many moles of I2 do we get? 1. So for every X moles of H2, how many moles of I2 do we get? X. Does that make sense? However much this goes up by, this is going to go up by the same amount. These are tied to each other. Does that feel okay? All right. So now the tricky one. Don't shout it out. I want you to think. What value should go here? How much does this go down by? Don't shout it out. Look at the equation and think. If this is going up by X, that's also going up by X. We said those are going up because they're the products. They're getting made. This is going down because it's the reactant. How much of it is going to get used up? How much is it going to go down by? Sarah, what do you think? It would. Excellent. How'd you know that? Yeah, very good. If we look at the equation, we can see there. So that's going to be my first little note, which is just use the coefficients from the reaction with X, i.e. 2X, 1X, etc., right? And products are being made, so we make those changes positive. Reactants are being used up, so we make those changes negative. So products are made. So plus X. Reactants are used. That was the oddest intonation of used I've ever heard. So subtract X. Does that make sense? Well now, at equilibrium then, what will the concentration be? Well, we don't know the number, but we can do a little bit of algebra. What are you doing now? Let's shut the computer off, please. We're doing this right now. All right? This is important stuff. Key lesson for the evening. I need you focused on it. What will the concentration be at equilibrium? What would the algebra tell us? It started out at 0.10, and it went down by 2x. So what would go in this spot? Yeah, it'll just be 0.100 minus 2x. One sec. Does that make sense? We don't know what the concentration will be at equilibrium, but we know it will be what we started at minus that change value, right? What will the concentration be here? 0 plus x, which we can just write as which equals x. Good. Likewise here, it would just be 0 plus x, which we can write better just as x. Okay. How's that feel? That's actually not really doing anything that isn't totally intuitive. This is just a way of looking at a table and saying, okay, if we let this thing go to equilibrium, however much of this we started with, it's going to go down at twice the rate these both go up, because looking at the equation, we use up 2 moles of HI to make 1 mole of each of these things. We're just kind of formalizing it with some math. Does that feel okay? Would you tell me if it didn't? Well, I hope you would. Yeah. Yeah. Eventually it will, right? So whatever x, that's an excellent question. The answer is, what value of x will let this get to equilibrium? And the only way to know that is we would have to know the equilibrium constant, or we would have to know an equilibrium concentration. Does that make sense? So in this case, if the equilibrium concentration of HI is found to be 0.078, what can we figure out? Well, if the equilibrium concentration of HI is 0.078, what could we say here? We could say the concentration of HI at equilibrium is equal to 0.078, right? But we also know that equals what? That also equals 0.100 minus 2x. What could we do now, team? Can we solve for x? What would you do? How are our math skills? So I'll clean this up a bit. We have 0.078. You might want to do this without the units, right? Just to make life easy. And we might even want to do it like a math guy, where we don't put unnecessary decimals. I'm comfortable with that. Does that feel a little cleaner?
Yeah.
Okay. What would you do next?
Or no, subtract it.
Okay, we'll subtract 0.1 from this side. We'll subtract 0.1 from that side. I like that. That will leave what on this side? Negative 2x. And over here, we should get negative 0.0... 22. Is that right? Okay. What do we do next? What would you do? Okay, if we divide negative 2 on both sides, that'll cancel here, right? And that should be trivial for us. That's going to give us an x that is equal to... Yep.
How did we get negative 0.22 subtract?
Try it. Do 0.078 minus 0.1. Get your calculator. Do the math. Don't ask me how we get an answer when you haven't done the math. That's silly and a waste of my time, right? If we disagree, that's a different answer. What'd you get?
I got 0.068.
Okay, so look here. 0.078, right? Minus 0.1. What do we get?
Oh, I thought there was 2 zeros.
Oh, okay. Yeah, that's fine. But try it again, see what you get.
Yeah, I already see.
Perfect, great. And now if we divide that by negative 2, what do we get?
0.0.
Very good. Okay. We get x being equal to 0.011 molar, right? So now can we go back to our table and fill in our final values that we know? Let's go back to our table. Now, at equilibrium, what would the concentration of H2 be? Well, we know the concentration of H2 was going to be x, right? But what's x? Okay, so 0.011 molar. What about the concentration of I2? What's it going to be? Okay. And then what will the concentration of HI be? We actually already found it. It was given to us. What is it? 0.078. Does that make sense? Being given only one of the equilibrium concentrations, we were able to figure out the other two. Does that make sense? And now, if we wanted to, what could we solve for? Which is good, because the question asks us to. We can solve for the equilibrium constant. Because what does the equilibrium constant have to be equal to? KEQ must be equal to the concentration of H2 times the concentration of I2. Someone else, finish it. Where's that? On the bottom. Concentration of HI, and it is squared. All right, and then can we just plug actual numbers into this at equilibrium? At equilibrium, what's the concentration of H2, did we decide? 0.011. Okay. What's the concentration of I2? 0.011 molar. Great. And what's the concentration of HI? 0.078 molar. And what do we have to remember to do with that? Square it. All right, everyone do this on your calculator. Everyone do it on your calculator. Write your answer down. We want to make sure we can use our calculators effectively, all right? Keep in mind, depending on your calculator, if it is a nice modern one that has a fraction button, great. If not, and you have to use division, then make sure you're using brackets, all right? 0.01. I'm using a bracket for the top of my fraction, 0.011 times 0.011, dividing, and then I'm using a fraction bracket for the bottom of my fraction. On this one, it doesn't really matter, but there'll be plenty when it does matter. And I mean, this is really 1.21 times 10 to the negative 3 times 7.8, 7.8 times 10 to the negative 2, so this should be times 10 to the negative 5, except it's going to get bigger. I'm surprised by that number. Oh, I forgot it was squared at the bottom. I'm fired. Yeah, perfect. So what is it? 0.0199. Did anyone get anything different, or how did we do?
Yeah, I just found it.
And how many sig figs do we actually have in this question? Only 2, right? Yeah, so it's actually 0.020, which is what I designed the question to come out to. I wanted to get a nice looking number. What's the unit on that? Why nothing? We have molar squared, and that's going to cancel with molar and molar. Cool. Excuse me. How's that feel? Is that okay? Not too bad? Do you see how the ICE table helps us just organize our thoughts? You could do the question without that, but the ICE table is going to help you conceptualize what you're looking at. How is the math on that? How's our algebra? Because this unit is, the algebra doesn't get too tricky, but there's a lot of it. Full disclosure. No, I mean, next unit's just like easier math than any of the other math we've done. Yeah, but it's like 2 formulas and they're easy. This unit's the mathy unit. Oh, he's not here. He's not here. He's gone. Crit's not here, man! Okay, anyway. Sorry? I'm sorry. Do you think they're calling Crit into guidance to criticize him for his poor attendance of my class? That's a good reason. I can't argue with that. In Thailand. All right. So we're going to do another example, and we're going to look at an example here where we actually have been given the equilibrium constant. This is going to be the most common thing you get because there's a big table of equilibrium constants where you can look up the equilibrium constants for all kinds of reactions. You often will know the equilibrium constant and be using that to predict the outcome of things. Does that make sense? So in this case, we have a new reaction we have carbon monoxide reacting with water in the gas phase to produce hydrogen gas and carbon dioxide. All right, there's our gas. What is our KEQ here? What's our equilibrium constant? We know that it's 0.83, but what's that going to equal in terms of our reaction? How do we write the KEQ expression for this? The mass action law statement. Okay, I'd probably just, given the order of it, go H2 first and then CO2, but that's fine. It is completely irrelevant which order you put those in. What else? Someone else?
CO bottom and then H2O on the bottom.
Okay, there we go. How's that feel? Are we comfortable with that step? We can write our equilibrium expression, and we can actually, since we've been given KEQ, we can say that this is true. And does it give us the conditions? At 700 Kelvin. Okay? And so these would actually all be the values at equilibrium. Specifically, these would all be the values at equilibrium at 700 Kelvin. Does that make sense? If you're not at 700 Kelvin, these values won't apply. All right. Suppose you start with 1 mole of carbon monoxide. Well, we've got our carbon monoxide here. We've got our concentration of H2O here, and we'll say that's in molar, that's in molar. We've got our concentration of H2 here, that's in molar, and our concentration of CO2 here, and that's in molar. That way we don't have to write the units in the table. Do you remember that? That if you write the units at the heading of a table, then you don't have to write them in every cell. That's nice for your math, right? To not have the units there, we can put them in later. So, what is it giving us as an initial concentration? I wanted to start with a nice easy number. 1 mole of carbon monoxide and 1 molar, I should say. 1 mole of H2O in a 5-liter solution. And this shouldn't say solution, actually. It should say container, because we're talking about gases here. Whoops. But that's okay. So let's start with that. What is the concentration if it's 1.0 moles in 5.0 liters? What is it? 0.20 molar, right? So, our initial concentration of carbon monoxide is 0.20. What's our initial concentration of H2O? 0.20. And we are assuming, the question doesn't actually say this, but we're assuming that the initial conditions are such that there's no product. So what can we write here? 0 and 0. How are we feeling so far? I put it in the heading, so I don't have to write it there. But you could, absolutely. All right, how's that? Not too bad? Okay. How are these going to change? Negative, negative, positive, positive. Good. Reactants get used up, products get made. What about the numbers? How many moles of everything? 1's all around. And then, obviously, because we don't know how many times that's going to happen, we have to put x, right? So these will go down by 1x. These will go up by 1x. And by convention, we typically don't bother putting a 1 with it, right? So at equilibrium, what will this concentration be? It'll be 0.20 minus x. What about this one? Okay, what about this one? X. What about this one? X. How's that feel? Is that kind of okay? Now, how could we possibly solve this? What do we know? We know that at equilibrium, we know that at equilibrium, 0.83 is equal to the concentration of H2 at equilibrium, which I'm often lazy about not writing, but it is important to remember that this equation is only true with equilibrium concentrations, right? Divided by carbon monoxide concentration at equilibrium and water concentration at equilibrium. So then we can say 0.83 equals what? Sorry? Okay, which is what? What's concentration of H2 at equilibrium? At equilibrium. X. Right? We're talking about at equilibrium. What's the concentration of CO2 at equilibrium? X. What's the concentration of carbon monoxide at equilibrium? 0.20 minus X. What's the concentration of H2O at equilibrium? All right, mathletes, what do we have here? We have ourselves a quadratic expression. Now, this one's actually really friendly. Oh, it's super friendly. Because this one has a little something going for it that they typically won't. Which is because I happen to give you something where all the starting conditions were the same, and it's a 1-to-1-to-1-to-1 stoichiometry. What's another way we could write this top right now? X squared. And what's a way we could write this bottom right now?
0.20 minus x squared.
Yeah, be careful though. 0.20 minus x all squared, right? This one is friendly. What can I do with this? Do I have to expand this one and use the quadratic equation? Or is there a trick we can use with this one? We can just take the square root. And you could move it first. I'm just going to take the square root now. All right? So if all of your x's are neatly squared, you can square root. It won't always be that way, but we don't have to do the quadratic formula on this one. We can take the square root. So we can take the square root of this side, and we can take the square root of that side. What's that going to give me on my next line? What's the square root of 0.83? Everyone. Guys, at every single step in this unit, everybody's going to pick up their calculator and punch things in before anyone tells me the answer. So everybody pick up your calculator, find me the square root of 0.83. You got it? Pick up your calculator and do it. All right? No freeloaders. Because inevitably then you get people come test time going, oh, I'll do this. And you're like, oh, well, we've only done 100 examples in class. Every single question, I want you to do the math. All right?
1.
What do we get? 0.911. Cool. And then what will we have on this side? X over. Yeah, always keep at least one extra sig fig while you're going, right? Sig figs are for final answers, not for middle steps. You introduce rounding errors. Always keep extra. All right, now how do we solve this? Yeah, this whole expression we want to multiply by, right? 0.20 minus x. That'll cancel it out here. We'll do it there, 0.20 minus x. What's that going to give us? Over here we'll have x. What will we have over here? 0.20 times 0.911. What's that? Hold up. Everyone do it. Okay, cool. And then what's the next thing? Be careful here. Negative x times 0.911. Minus. Okay, cool. What would you do next? Hold up. Give everyone a chance to think. Give everyone a chance to think. We're going to do a little bit of thinking. I really want to encourage you to kind of do your own thinking on math in this, so you're not just following along with other people's math. Because if you just follow along with other people's math, that's how you don't actually learn how to do it. So I want you to look at this and think, what's my next step? I need to get x all by itself. Do I have x all by itself right now? No, in fact, I've got an x over here all by itself. That's great. Unfortunately, I have another x hanging out here. So what am I going to have to do with that? That's what I would do. So to get rid of this x, I have to, right now it's being subtracted. The opposite of that is add. What am I adding? Good. What I do to one side, I've got to do to the other. So what's my next line look like then? Over here, x plus 0.911x is how many x's? No. If I have $1 and you have $0.911, if we put them together, we don't have $2. How much do we have? Beautiful. So how many x's do I have? Beautiful. Does that make sense? Awesome. And what remains on the other side? 0.1822. All right, we're almost there. What's our last step? Yeah. Yep. That's because the number isn't written here, but if you have just an x, how many x's do you have?
1.
Yeah, 1. And 1 plus 0.911 is?
Well, why would it not be 0.911x squared?
Because you're adding. You're adding. You can't square something by adding. X times x would be x squared. X plus x is 2x. And listen, it's very normal to get screwed up with this stuff. Maybe you haven't done it for a while, right? If math was a long time ago, you'll get some time to practice, but not as much as you'd like. So practice hard. What's our last step here? How do we isolate the x? Very good. So we divide that by 1.911. We divide that by 1.911. And when we do that, that obviously cancels. So we're going to get something equal to x. And of course, I don't know how your 0.1822 times table is. Mine is bad. But that is almost like 1 divided by 10. This is going to be a little bit less than 0.1. 0.095. That makes good sense. And that's a 2 sig fig answer, which is what we want. We want to end on a 2 sig fig answer, right? So that's good. That's our x value. Now that doesn't answer the question, but it gives us all the information we need to answer the question. And don't forget to answer the question. We just solved for x. That's good. But of course, the whole point of solving for x was to do what? Was to find the equilibrium concentrations. So now we know that this is going to be 0.20 minus x, which is 0.20 minus, which is going to be what? Very good. What will this one be? Okay. What will this be? Good. And this one? Excellent. How is that? Does that feel okay? Nope. Eventually. No, I want them focused. The second you hand those out, they'll be not focused. This stuff's important, right? Okay. Any questions about that? Now, that's as easy as it gets because that one happened to have a nice square root on both sides, so we could just take the square root. That won't always be true. Okay, for our next example, we're going to have to do a real quadratic. Can we handle it?
No.
I think we can. Let's go. All right. Here we have hydrogen gas plus iodine gas gives us 2HI. And we're not going to start with the same concentrations this time. We're going to start with 2 moles of hydrogen, and we're going to start with 3 moles of iodine. Now we're at least going to use a 1 liter container, so that makes the math easy, right? Because the concentrations will just be, yeah. So ready? We can say that the concentration of H2 in molar will be what? Initially, how much? 2 moles in 1 liter will just be 2.00 molar, right? What about the concentration of I2 in molar to start with? Yeah, and again, 3.00 moles divided by 1.00 liters will give us 3.00 moles per liter. And how much HI should we have initially? It doesn't tell us, but we're assuming since those are the only two things that were put in the vessel, then there is no third thing, so the concentration will be 0. Yeah. Not in the table. We're going to in the expression, and in fact, if you want to write that to begin with, we could say that the equilibrium constant, which the question tells us what the equilibrium constant is, what is it? Equilibrium constant is 25.0. And what would that be equal to in terms of mass action, in terms of our... Very good. Okay. All right. So that doesn't mean that this is squared. Concentration is still just the concentration. But when we go do math, we're going to square that value. Absolutely. Now, what will the changes be? Give me just the signs first. What's going up? What's going down? H2 is going to go down because it's a reactant. What about I2? Good. Why? It's a reactant. What about HI? It's going to go up. Okay, now give me numbers. What will the number be here? 1x, 2x, 3x, 5x? 1x, okay. 1x and 2x's. Great. How'd you get those values? The coefficients. That's how much gets used, right? Okay, good. Now, that means at equilibrium, what will this be?
2.00 minus x, 3.00 minus x, and then 2x.
2x. Okay. Now, what can we do? We can sub these values into 25.0 equals concentration of HI squared over the concentration of H2 times the concentration of I2. Does that make sense? We can use those values, which means we're going to get 25.0 equals, and then a nice fraction line. And what's going to go at the top? 2x all squared, right? What's going to go at the bottom? What's going to go in this first bracket? H2. Great. And I'm going to give you my patent blessing to ignore unnecessary decimals in your math if you want, right? It'll make you less likely to make an error, I think. What's going to go in for I2? Great. Now, to be clear, this just looks like a grade 10 math problem. Right? Not a particularly nice one, but hey, guys, we can do this. So you're going to have to expand everything. Now, I would probably get these out of the fraction to begin with by putting them on the other side here. Does that make sense? I would probably, though we can wait. Do you want to expand it first? 6 of one, half dozen of the other. Do you prefer to expand first? Yeah. Okay, let's do that. What's the top expand to? Be careful. 2 squared is 4. X squared is x squared. Is that comfortable? Okay. That gives us this. Now, this has to give us down here. How do we do it? 2 times 3 is, okay, now careful here. Negative x times 3 is negative 3x. Okay. Negative x, and 2 times negative x is negative 2x. All right. 2 times 3 is 6. And then negative x times negative x is negative x times negative x is
Positive x.
Positive x squared. And you're right. You're absolutely right. What does this come to? Very good. So I'm going to probably even put them in order. You know what I mean? Just to make life neat. What is the proper order for these? X squared minus 5x plus 6. That's probably how I would approach it. You know what I mean? If you're you don't have to. You can leave it in any order you want, but you might as well make it neat, right? Now, what am I going to have to do with that whole thing? I'm going to have to move it to the left. And in doing so, everything's going to get multiplied by 25. So what will my new expression on the left be? 25x squared minus, what's 25 times 5? Yeah. And then what's 6x? Or what's 6x? What's 6 times 25?
150.
Good. What's going to remain on the right side? 4x squared. How's that? Does that feel okay? Do you feel like you're in math class? All right. We're almost there, team. You're almost there. What would you do next? You would do what? Could do, but it's not really going to be helpful. Wouldn't be wrong. It would work. You could do, but you're just going to have to put it back in, because what does this thing have to equal if we're going to use the quadratic equation? Thing has to equal 0, right? Do we remember that? Quadratic equation tells us that we can solve a quadratic as long as it's set equal to 0. So what am I going to have to do to make this equal 0? So needs to equal 0 to solve, right? Therefore, we're going to get rid of this 4x. What's the opposite of 4x squared existing? Subtract it. We'll subtract 4x squared. Which of these terms does that change? Yeah, the 25. What's it going to be now? 21x squared minus 125x plus 150 equals 0. Okay. How's that? Does that feel semi-okay? We okay? We're okay? I'm okay. Do we follow the math there? Do we get from here to there? Any questions about the math there? Okay, now, for us to go ahead and solve this, we could just say that A is equal to what? A is equal to 21. What's B equal to? Negative 125. What's C equal to? 150. Okay, and then we can say that X will just be equal to, let's go very carefully, negative B, right? So what's negative of negative 125? 125. Plus or minus the square root of what? Negative 125 squared. Minus 4 times 21 times 150, right? Because it's AC all over 2 times 21. All right, put that in your calculator. You've got to be able to do a quadratic cleanly in your calculator. One step. Look at me. None of this calculating little bits and pieces garbage. You've got to be able to do this in one step. All right? So I'm going to do it myself here too, see if I don't screw it up. I'm doing a bracket for the top. If you have a nice new calculator that has a fraction button, for God's sakes, use it. It'll make your life so much easier. All right. I think these seem right. I think I got it. So try yours. Is that what you got? Great. So again, guys, you got to know how to put a quadratic into your calculator. So practice. Give it some shots. Try it out. I'm going to try... Boy, do I have enough tabs open? I think I need some more tabs open, team. I can't handle this right now. New window of tabs.
Why do you keep so many tabs up?
Quiet. Yes.
What, in the mode section, what do I have to put to not get fraction answers?
There should be a change button rather than changing your mode button. That calculator is giving you a fraction button. An answer here. Come here. We'll just reset it.
With the button on the back, right?
Yeah. Yeah. Do you know where that is? Just hold that for a few seconds. And keep in mind, if you've got Desmos in front of you, it is. You should be able to use your hand calculator too, to be clear. But Desmos lets you cheat because look here. Do you know that? Does everyone know this? Does everyone know that in Desmos you can define variables and then use them? So I can say a equals 125, b equal, but you got to get it right. What does a equal? 21. A equals 21, b equals negative 125, c equals 150, and then you can just use them. Negative b plus the square root of b squared minus 4ac all over 2a. And then you can do negative b minus the square root of b squared minus 4ac all over 2a. Now listen, don't cop out. You should know how to use your calculator to do this. Do you know what I mean? But if you're doing an assignment, should you check your work? Absolutely. But make sure you can get these same two values on your calculator, okay? Try it out. If you can't, yep.
So doing it? Is there just like a name? Okay, so I'm guessing psi for getting scientific answers?
Oh, interesting. Yeah, but you don't want scientific. Show me. I've just never had those yellow calculators give me a fraction. I didn't even know they could. But that's golden. That's great. So now, to turn that into no worries. So now, go math, decimal, and it'll do that. That's awesome. Nicely done. Beautiful. That's great. And then just go up and do the same, but instead of doing plus, you'll do minus. I didn't know.
Permanently a decimal?
Sorry?
I got it permanently a decimal, though, right? That's what you said?
No. Just when it gets your answer, press math to enter, and it'll turn into a decimal. That's all. I had no idea you could use the fraction input like that in those yellow calculators. You just taught me something. You have to show me that after. That's way better. Way better. Did everyone get these two answers? Okay, now, hold up. How can we have two different answers for x? Right, so the parabola gives us two answers because it's math. Are there actually two answers in the real world? So which one of these is the answer? And I want you to look at our ICE table, and it's going to jump out at you. All right? Look at your ICE table. Think about what we are trying to find. We're trying to find the concentration of H2, the concentration of I2, and the concentration of HI. And the answer is either 2.00 minus x, 3.00 minus x, 2x, such that x equals 4.2, 4.3, or that x equals 1.7. Which one of those is correct? Why?
Because H2 and I2 are supposed to be going down. If it's 4, it's going to be going up instead of down. I think.
Not going up, but you're exactly on the right track. What would 2.0, well, yeah, no, sorry, you are right. What would 2.00 minus 4.3 be? Negative something. Can you have a negative concentration? That doesn't make any sense. It's absurd. So in philosophy, we have a fallacy called the reductio ad absurdum fallacy. We can say something isn't true if it leads to an absurdity. So x either equals 4.28 or it equals 1.67, but it can't equal 4.28 reductio ad absurdum. It can't be 4.28 because that leads us to an absurd conclusion. Does that make sense? So, from these, what? You hate Kate?
Yeah.
Don't hate Kate. I love Kate. You're not allowed to hate Kate.
Don't look around if anybody else is reacting. Stop. You're older than this. He said 1.67. Now she's looking around.
Oh, I hate Kate too. All right, never mind. Sorry. I thought I didn't hate Kate. Kate, I really thought I loved you, but in this moment I've learned something about myself, which is that I hate you. Yeah. No. That's a great, that was a, no!
I looked up to see cartridges.
1 second. Yeah, you can now.
I
You
can?
can. Yeah, you can.
Oh, I thought you were
That's
saying
okay.
no to me. I'm scared.
No, I was saying no to her. No, you're good. You can
Oh.
hand those out. Yeah, listen, it was a wonderful question, so everybody listen to it. The question was, can we always just ignore the one with the plus, which would be a possible conclusion from this? It won't always be one or the other, so you've got to check both, and one of them should be absurd, though. If they're both reasonable, that can actually happen in certain situations. That would mean there's two possible equilibrium states, which can happen. But in this case, one gives us... Now listen, we have to actually answer our question. What is 2.00 minus 1.67? 0.33. Good. What is 3.00 minus 1.67? 1.33. And what will this be? What is 2 times 1.67? Cool. I guess it's a 4, actually. How's that feel? Not too bad?
Wait, so are we going to do a question that's going to have both
I don't think you'll come across any where you get 2 valid solutions, but you'll definitely come across questions where the other one is the correct solution. We only have 1 minute left, but don't worry, you will in your homework. So there's some practice questions in here, guys. I can't stress enough. Don't skip a day's homework right now, all right? This unit's coming hard, like a freight train. And you want to jump on the freight train, you got to keep running with it, right? Try to jump on the freight train, but you're going way slower than it. You know what happens? You just got yourself run over by a freight train. That's how that works. So you got to run hard, all right? You've got to. Yes?
So like this unit is going to last till like halfway through December or so. So are we going to start a new
No, we're going to finish this pre-Christmas, but trust me, that's going to be plenty tight.
Alright, so like this unit is going to last until
Until the 19th.
Yeah.
And I'm not going to give you a test on the day before the Christmas break starts, so until the 18th. Unless you guys really want that extra day, but I would feel like a real monster if everyone else is being like, I'm showing holiday movies. We're decorating candy canes. We're playing video games. My students are writing an equilibrium unit test. Do you see? I would feel like a real Scrooge.
So what you're saying is on the 19th we get to do fun day.
Oh, on the 19th, we're going to chill out. I thought I would bring you all cookies and baked goods and we would consume them. Yes. And watch a movie,
Every
perhaps.
other time I've had you before the Christmas break, you're like, we're not watching a Christmas movie. We're doing a lesson today.
No, I never the last day. Never the last day. I am Scroogey. I'm not that Scroogey.
Well, are we doing like assemblies and stuff, or am I lost?
Yeah, probably in the morning. But then afternoon, usually in the afternoon, you're supposed to report to your classes, but it's just chill. But I figure here we'll probably put a Christmas movie on, and I'll just feed you.
Second period is the assembly.
Sorry,
Second period
is the assembly? Nice. Are you guys planning on that?
Yeah.
Is it going to be the usual Ventnor show?
Nope.
No.